Hello, I've shared the screen. Is it visible to you? Hello, hello.
Yes, sir, it's visible.
Okay, fine. So I think your section has more than 60 or 70 students, 60 at least. So I see only a few students join the classes. Why it is so? What is the problem? See, C section they have 80%, 80 student, 80, 90 student. They join the class, but your class I don't know why so many students bunk the class. Anyway, so in the last class we actually came till this point. We completed the DFS search, and we discussed about the predecessor subgraphs that we obtained from DFS traversal. Okay, so basically as soon as a new vertex is found out by the search algorithm, so we add the predecessors. That means the vertex through which the current vertex is discovered. For example, in the figure, it discovered y vertex y. The DFS discovered vertex y through V. So V become the predecessors of Y. Similarly, Y become predecessors of X and so on. So in this way, the predecessors ages, basically tree ages, those are in the are considered to construct the predecessor subgraphs, and this can be put it as a table also. And as soon as you execute the algorithm, that algorithm actually store all those predecessors value, and we can immediately construct the tree. Okay, so once you run the DFS algorithm uh, for all the components, basically you can construct the predecessors forest as well. Okay, so this is something similar to that you have done your second assignment using BFS tree. Here thing is that DFS tree. So here uh, uh, some important characteristics is there for DFS algorithm. So in fact, if you look at other books, they usually don't use the discovery time and finish time, but in Coleman's book actually they use this particular notion, particular properties to characterize the DFS algorithm, and also it has some nice application. One of them is the topological sorting of the vertices of a directed graph. Okay, so we'll see today how this finish time can be used to determine the topological ordering of the vertices. So now let us see the parenthesis theorem is tells about, say you have, after you explore the graph, after you explore the graph, uh, all the vertices have a start time and discovery time and the finish time. Okay, so now they show certain parenthesis properties. We call these parenthesis properties because suppose if two vertices belongs to the same connected components, then their discovery time and finish time form an interval, right? So those intervals actually contained in our each others. So one of the interval is contained completely in others interval of the other vertices in the same connected components. If they belongs to different connected components, that means they are actually belonging to they have a disjoint interval. Okay, so here this property is put it as a theorem. So there are three cases can be possible for a directed graph or undirected graph. Once you perform the DFS on the graph, then you can draw these three conclusions. That suppose u and v are two vertices of the graph, then one of the three conditions three properties hold. First one is that it tells that they are entirely disjoint. Say interval for u and interval for v, they are disjoint, and neither u nor v is a descendant of other in the depth first forest. So in fact this occurs when they belongs to different connected components. Okay, so once we suppose we call this uh, DFS for this graph at the vertex u, so it will discover, actually it will label u v y x, and it will not discover w and b because there is no s from one of these vertices x u v y to any vertex in the rest of the graph. That means w and z are not reachable from u, so those vertices cannot be discovered by DFS here. So what will happen, that you have to, that another call will happen at w. So and if you look at in the first part that is discovered by the first call, which are vertices which are reachable from u, they had this actually uh, discovery time and finish time has certain overlaps. Okay, and for u v w or x, sorry, u v x or y, you look at the interval. So intervals are basically here written as as a oblique. So for x, so x comma d is 4, x comma f is 5, f find finish time, x comma f is 5. So this interval is disjoint with the interval with w. So 9 comma 12 is the interval for w, 10 comma 11 is the interval for b, and so on. Okay, so this is the case when your vertex is basically here one of these x v u y, and another set of vertex may be w and z. So they will show completely disjoint, and that's why there is no descendant or ancestor relationship there. Okay, second case says that interval for u is contained entirely within the interval uh, of v. There is a typo here, you don't need put and here. So v dot v u dot d comma u dot f is a subset of v dot d comma v dot f. So that means we can write in this fashion also, that v dot d less than, strictly less than v u dot d, strictly less than u dot f, strictly less than v dot f. Okay, so in this case u is descendant of v because u is contained within this interval for v, so u must be discovered at later time than v, so that's why it's become is a descendant of v. So it's a successor, you can say successor or descendant of v. Okay, in the depth first for tree. So in this case, so v is a descendant of u, so that's why 2 comma 7 entirely contained within interval 1 comma 8. Similarly, for y 3 comma 6 is the interval which is contained within entirely within the uh, 2 comma 7 or 1 comma 8, and so on. So all the vertices are reachable from u have the interval which is totally contained in the u. So it will form kind of a nice manner we can put into a parenthesis basically. We'll so one such case. So interval uh, so this and will not be here. So interval v, interval for v is contained totally within the interval of u. Okay, and v is descendant of e. So basically 2 and 3 uh, they are basically same statement, but with respect to u and v it looks different. So if we just interchange the role of u and v, so condition in 2 is same as condition in 3. Okay, so that's why when interval for v is contained total in the interval of u, then v is the descendant, that means v is discovered later. So these things can be put into into in a nice manner as a parenthesis. So in fact, you can look into the Coleman's book, elementary algorithms, that chapter I have uploaded. You can look into that for that proof. So here uh, you try, you just get the idea that what actually happened. So this will be used to, these properties will be used to classify the edges, different type of edges of a graph that explored by a DFS traversal. DFS traversal. So here we have taken another graph that we call DFS at S, and another call would be at T. So in fact, there will be two such call. It's a directed graphs, and here, if we just just redraw the forest, DFS forest, for these two uh, part that is discovered by the DFS algorithm, and corresponding start time and finish times are written. So the start vertex, which will have the interval length will be longest. So its discovery time is earliest, so it is discovered just before any other vertices, and all the reachable vertices from S has the discovery time lesser than that. So that's why Z was discovered through S. So Z is basically successor of S, and S is the predecessors of Z. So that's why interval for Z is entirely contained within the interval of S here, so which is shown over here. So 1 1 9, start at 1, end at 9, so sorry, end at 10 for S, and then for Z it is start time is 2 and end time is 9, and similarly Y, W and X. Okay, so I see that it forms a, if you put the parenthesis just like the shown in the figure, that it forms a well balanced mathematical just like a mathematical expression, parenthesized expressions. Okay, so it tells you something related to, stack fast in fast out. So whenever some vertex discovered, uh, it has to be finished fast basically. So last one, sorry, the last one first. Which one has discovered last will finish first. For example, in the search, in the exploration that start at S, X is the last vertex which is discovered. Okay, that's why it has finished fast. So that's a basically kind of stack. And if you remember that Polish expression, that evaluation of the Polish notations for mathematical notations, so there also similar things are there, right? So so in fact DFS, when we use the recursive routine, that actually implemented by compiler, the recursion implemented by the compiler, and compiler uses stack, system stack. When you do function call, that's a system stack is used there. So in the function call also, when you call a function, and that's actually return to the calling functions after it's finished. So there is also nested call of different functions, and that will also show similar kind of things. So their structure is same, although we do different type of computations and all, but there is something similar to that. So functions call actually occurs in a DFS manner. Okay, so function call in a programming language, uh, in the recursive call also, they occurs in a depth first manner. And similarly for another component here, T, start vertex is T and descendant are U and V, and they also show the parenthesis property. But here you see the intervals for any of these vertices T, U or V do not have any proper intersection with the intervals of any of these vertices from the previous one, that means S, Z, Y, W and X, because they are discovered through different calls to the DFS at different start point, start vertex. Okay, so uh, this DFS actually uh, give you uh, you know classify the ages in the graph. So as you have seen in the BFS breadth first search, we have seen back age, tree age, and so on. So here also you can have in a DFS also you can have a predecessor subgraphs, and as you discover different vertices through the edges, so you can classify the edges as follows. So tree edges are edges in the depth first forest. So after you execute the BFS or DFS algorithm, so all the tree edges, so predecessor subgraphs or DFS tree, depth first tree, uh, all the edges actually called the tree edges. So an edge u comma v is a tree edge if v was discovered through u. That means v was immediate successor of u in the breadth first search. So back edge is an edge. Back edge are those edges u comma v connecting a vertex u to an ancestor. So ancestor means that v was discovered before u, in fact. Okay, and so it may happen that there is another edge from u to v that found in the later time in the depth first search. So we can uh, find that is later time. So if he was discovered and then after some time u is discovered, but we found that there is a s from u to v. So that's called a back edge. And as before, back edge means existence of a cycle, and we we don't take such edges actually. We don't include those edges in the depth first in the predecessor subgraphs or in the depth first tree. So we, by convention, we also take self loop as a back edge as well. Okay, so I think there is an image over here. So you see over here that in the search that v was discovered, and then y is discovered through v, and then x is discovered through y. And when you process x and its adjacent vertices, the outgoing edges you look at to discover a new vertex. But you see there is an outgoing edge that takes x to v, but v is an ancestor, right? Because it was discovered before x. So that's a back edge, we call a back edge here. And all the shaded edges are forward edges or tree edges, sorry, not forward, it's called tree edges. So these are all shaded edges that form the predecessor subgraphs or the depth first tree. And also there can be edges from a vertex to another vertex uh, that can forward edges where v is a descendant. So here, for example, x is a descendant of u. X is a descendant of u. What will happen that in the DFS traversal from u to v, y to x comes, and there is a dead end. So it backtrack up to it's come back to u, and again it's look at all other remaining adjacent vertices of u. So there is an s from u to x. So that x is already discovered. So we do not go through. Sorry. So such edges are called forward edge. So any edge from an ancestor to a descendant is called a forward edge. So this can be characterized using actually discovery and finish time as well. So forward edge, tree edge, back edge, and forward edge we have got. So whatever other edges left out are called the cross edges. All other edges which are not a tree edge, not a back edge, or not a forward edge are called the cross edges. Say for example over here that there is an edge w to c, but y is already discovered and there is nothing to do. So such edges is called, is neither a descendant nor an ancestor relationship is there. So basically such edges are called the cross edge. Okay, and there is a self loop over here z to z, so that by convention we use we say that is a back edge, and all the shaded edges are forward edge, sorry, tree edge. So there are 4 type of edges, and you may be asked, okay, find out all the back edges and forward edges. I can give you a small graph like this, and I can ask you, so label all the edges according to this particular depth first search. Okay, so so in a some observation is that in a depth first search of an undirected graph G, every edge of G either a tree edge or a back edge. Okay, so in case of the undirected graph, so directed means you can go from one from start point to some end point of the edges which are directed edges. You cannot go in the reverse direction, right? So that's why uh, there is certain difficulties there. But when graph is undirected, basically you can go in any directions, and basically the edges which are left out after traversal, that means all the edges belongs to the predecessor subgraphs that we constructed by using predecessors relationship. So those are basically tree edges, and then remaining edges are back edges. And note that all the back edges will form a cycle. So if you modify the DFS traversal as you did in the BFS in your assignment, so if you just manipulate something over here, the line number 5, so if it is white, then you do something. So if it is not white, then you have to put appropriate condition to identify where the what this is, what type of age of is this, say v u to v or v to u, what are the type of ages there. Okay, so from there you can identify, actually you can label all the tree edges here, tree edges as well as back edges. Okay, so okay, so yes, so I give you here some homework exercise for you. Rewrite the procedure DFS using a stack to eliminate recursion. So why it is required that we don't use recursion, we should replace recursion. Can somebody answer? Do you know that difficulties with recursion? It's very easy to understand. It's very too easy to write the code in a language that support recursion like C. Now all the modern programming language actually support recursion, but when in Fortran 99 there was no recursion at those time. Fortran 2000 they have included the recursion. The compiler actually provide the recursion. This is a facility given by the uh, language. But can anybody tell what is the difficulty with the recursion? Anybody? Okay. So so in the data structure course you should have done that. Anyway, I tell you that. So recursion, that I just told you, that when you there is a function call, so compiler actually put all the context uh, to the execution context, programming context to the system stack, because once the function is completed, return to the calling function, so that context has to be restored. So it could be local variables, the value of the local variables, it could be program pointer, program counter. Program counter is the register value that's hold the address of the next instruction to be executed. So once it come back from the origin call function, that context has to be restored for continuing the execution. Okay, so depending on different what are the variables are there and things like that, there could be lot of content that has to be put into the stack. Okay, so so stack, if there is a lot of calls, just example the recursive calls, for a recursive call like DFS, the the system stack depth of the system stack can goes up to thousand lakhs also. if the graph is very large, say it contains a 100,000 of vertices. Okay, so definitely recursive call is going to overflow the system stack even if you have 8 GB or 16 GB of RAM. So you just can make a simple example with computing the factorial n, where n equal to 50 or 60. Even for 50, if you just compute the factorial using recursion, then it won't be able to compute it. There will be overflow. So system stack will be finished. So operating system will actually stop that program and exit. Okay, so that's why we sometimes be very careful when we write program, and for what purpose, what to do the input size and all. You have to think about that as well. Just like in social network graph, say in a Facebook or in a LinkedIn, there will be millions of users. So number of vertices means every user is a number of vertices. Then it could go up to millions, many millions, hundreds of millions, right? So recursion is not a good option there. So how to do that? So I'll give you some hint here that you should follow. I'm giving emphasis on these two algorithms because these two are most vital algorithm, that most fundamental algorithm is graph. All the algorithm are, most of the algorithms based on this traversal. Until and unless you export the graph, you cannot do any more computation. Okay, so here you see that there is a recursive call over here. That means you have to maintain a stack. So initially the stack is empty, and your actually execution starting at the point line number 3, right, for the recursive part. And then for every adjacent vertices of you are checking its color, and if it is white, you are actually setting the or updating its predecessors value, and also you are calling the function. So calling means it's a push operation. So you put the vertex v into the stack. So what you will do that, you first at the after the line number 3, you push the vertex u. So see, this is similar to your BFS algorithm. Okay, it's similar to your BFS algorithm. So there we have used a queue of vertices. Here will be used queue of vertices also, and all the vertices which are color gray, they are in the stack here. Okay, so after line number 3, you perform a push operations. So push the stack, suppose s is the stack, s comma u, and then you, instead of for loop here, you what you will do that, you insert a while loop before the for loop. Okay, so there you will do uh, a while, execute while the stack is non-empty. So initially you have put one vertex in the stack, so it is non-empty, so it start executing. And then first instruction will be the pop operation. Pop, that means take the front elements, top elements from the stack. So that will be your first element actually that you have given in the stack, that is you. And explore is adjacent vertices. As soon as you get it one, you make a push operations. Okay, so it will be pushed onto the stack every time you encounter a white vertex. And then when adjacency list is completed, so basically it will just go back to the while loop again and see whether stack is empty or not. So if it is non-empty, take the front element. That means whatever you pushed into the stack, it will be taken out. Okay, and it's done. So after this over, that basically uh, you make the vertex black and all. So basically you have to I just told you a few hint that the way you have to implement this using stack. So you have to rewrite the DFS visit algorithm using stack. Okay, so just give a thought on it and try to do that. It's a good practice, and it will help you a lot when you use the DFS algorithm for your problem solving. Okay, so if you do your project or anything that related to graphs where you are using graph traversal and not all, so it will be used there. Okay, so so that is the idea that I gave you. So you should try it out. Okay, next exercise is that, so that is u comma v. So basically here what we want to do, that we want to classify the ages based on their start time and finish time after we perform the DFS. So suppose you assume DFS is done, and now you want to classify the ages according to that the definition that we have given for a forward or back, the tree edge, back edge and cross edges. So there are three such conditions. If they satisfied this, you can actually immediately you can classify them. Okay, so in fact during execution of the, if you design your BFS algorithm properly, then during the execution of the algorithm you can also classify the edges, but we can also characterize the edges based on the finish time, start time and the end time, the discovery and finish time. So tree edge or forward edge, if and only if the u dot d v dot d, so they are in strictly increasing order. So v is a descendant of u, so that's why the interval for v is fully contained in the interval of u. Okay, so this is the interpretation. And back edge is basically when the interval of u is fully contained in the interval of v. Okay, so I think it should be strictly less than, because there won't be any equality. The way we have used the start time and end time, so it won't be equality. So cross edge will occurs if uh, the discovery and finish time, the interval for v is before before the interval of u, and they are totally disjoint. Okay, so these three conditions you should follow the definition and try to prove it. So they are if and only conditions, and that's why you can use them for classification. Okay, the third exercise is modify the pseudocode for depth first search so that it print out every edge in the directed graph G together with its type. So what modifications, if any, you need to make if G is undirected. So first you have to do it for the basically the modification of the algorithm for reporting the edges and the type. And suppose if the graph is undirected, so what will be the modification? So for undirected graph, actually you will have two kind of edges. One is tree edge, another is back edge, right? But in a directed graph there could be the above three types of actually four type of edges: the tree edge or forward edge, back edge and cross edge. Okay, and the fourth one is the give an algorithm that determines whether or not a given undirected graph G V comma E contains a cycle. Your algorithm should run in big O of number of vertex, so linear in number of vertex basically, and which is independent of E. So graph is undirected. Your objective is to find out whether it has a cycle or not. Okay, so how to do that? So I will give you the idea here, how to solve it. Okay, so suppose you have the graph v comma e, v g comma e. So v is the vertex set and E is the edge set, and g is acyclic uh, if and only if DFS yield no backage. So we have seen one result actually. So if there is a backage, there is a cycle, right? So what we will do, that we try to find out, we call the BFS on G. So DFS on G, so basically there may be multiple call. So uh, so G may be connected or may not be connected, but acyclic, that means G may be a forest. Okay, so or maybe a tree. If it is a connected, then the, uh, then acyclic means it's a tree. So what is the number of ages there? Number of ages could be, then if it is a forest, or if it is a tree. If it is a tree, its number of ages will be number of vertices minus 1, right? If it is a forest, multiple connected components are there and it's acyclic, then it will be n minus, so number of vertex minus number of connected components, right? So that should be the number of edges. So basically, in any way, so your algorithm DFS will run in big O of n plus m. So m is basically also bounded by a number of vertices, the number of edges. So that's why if the graph is already a acyclic connected graphs, acyclic connected or disconnected anyway, so it won't take time which is greater than big O of v. So it's a linear time in vertex. And another thing, that what will happen, suppose it has more edges and it's not acyclic. If not acyclic, there is a cycle. But my claim is that as soon as you find a back edge, that means a cycle. And as soon as that happened, that means you exit your algorithm from there. You don't need to explore all. So if you just look at the DFS algorithm, that is execute, you know, say, explore the graph using the adjacency list, adjacency relations, and every discovery of vertex means also discovery of an edge. Okay, so as soon as there is a back edge, so that means you, that discovery, if it contains a cycle, it cannot go beyond the time n, right? So that's why this algorithm will run in big O of v time always, because because if there is such package, that means at that time you discovered how many edges, basically that number of edges is bounded by number of vertices in the graph. Okay, so basically what you will do, that I'll go to the pinpoint location here. So basically here again, as soon as there is a, say in the line number 5, if you have a color of v is basically a gray color, right? So or a black color, so there may be a back edge, right? So if v is not descendant of u, v is v is not ancestor of u. Wait 1 second. It may happen that, say, through you discovered v, right? Now you look at the uh, color of v. So if the color is gray color, so gray means it's already discovered, so it has a predecessors. So uh, these predecessors, if it is you, then you cannot do anything, right? So we do nothing. So if it is not predecessors, if the predecessors of v is not same as you, okay, then what will happen, that you can say this is a backend basically. So this is quite similar to the DFS algorithm, BFS algorithm also. So you can, even after execution of the DFS, you can use the conditions of backends. So then as soon as there is a backend, so you said that there is a cycle. Hello, can you see the slide I have shared? Is it visible? Hello, can any of you can confirm me? Okay, okay. So what I was discussing and suddenly just logged out. So here that there is a back edge means there is a cycle. So if there is no back edge, then there are only three edges. Okay. So hence the graph is acyclic. So thus we can execute the DFS on G, and if we find a back edge, then we can report that the tree has a uh, cycle. Tree is not acyclic. The graph is not acyclic, and this will run. So finding a back edge basically will take big of uh, time, big O of mod V. So mod V is basically size of V, number of vertex. So that time. So in linear time, in number of vertices, we can actually find out a cycle if there is any cycle in the graph. Okay. So that's why this algorithm will run in linear time. So as I said earlier, that for this course you keep a notebook, and all the exercises I give you, you try to solve them and write your solution on the notebook, so that it's a learning, as well as it will help in your exam also, so for doing assignments, and at the later time in your BTech course, when you need the tree or this type of graph theoretic formulation for your project or all, so you can again come back and see for your placement and others for interviews. So you can look into the note, your note, and you can easily understand because you have written those notes, right? So you have probably read many times, so it will always help in the very long run. Maybe for next 10 years you will look into those notes again and again. Okay. So very important. So now we see another application of depth first search that we call a topological sorting. Uh, so you have seen the sorting of numbers in your data structure course, right? So sorting means, given a sequence of numbers, you want to arrange them in the increasing order or decreasing order of their magnitude. And you have done uh, the binary search also there, right? So for binary search, you need to have a sorted array of numbers, and uh, that's why you need some algorithm to arrange them, right? So here in the for sorting problem, you take the magnitude and you do that. Basically you put all the numbers on the real line, right? So there's a number, so always you can put on the real line. So now graph, there is no such real line concept, right? The vertices are some entities, right? They are not real numbers. So we sometimes wish to give a partial order, or ordering, linear ordering basically. So partial order is a kind of relations that we use. So here also topological sorting is will give a partial ordering. It's one kind of ordering of the vertices, so that we can put onto a line maybe. Okay. So basically we look for such ordering, such that, say, we arrange in a line, and such that there is an edge from vertex u to v when u appears before v. So in the ordering u appear before v, then there can be a edge, directed edge from u to v, but there cannot be a edge from v to u. In reverse way there cannot be. So that's why usually what we take as a directed graph for topological ordering. So in an undirected graph, actually edge means two-way direction, right? We can go in any way. So there actually we cannot use topological sorting there. In fact, topological sortings are used for directed graphs, that that represent actually for dependency. So if there is an S from U to V, means actually we are representing something that U is dependent on V, or say V is dependent on U. So it depend on the interpretations. For example, in a computer system, you have many programs running, right? And they are looking for resources, system resources, CPU time, memory, uh, network bandwidth. Suppose you wrote a program that's reading input from keyboard, so there is an interrupt and it's wait for the input that user gives. So you type the input and make enter. So the input output controller actually they take this value and put it in a memory locations, and then it give an interrupt to the program. Okay, the input is ready, you can take it from the system buffer. So that from the memory buffer that program read that value and start execution. So it's a dependency is created. There are many processes running on the system. So it may happen that everybody is looking for some resources in the system. So we can give an arrow from say for every resources and every say process in the system. You can construct a graph, dependency graph, that a process P is dependent on another process. It may happen. So if P1 is dependent on P2, you can give a arrow that is from P1 to P2. Again, P2 may be dependent on some printer, another entity. So there is an arrow from P2 to a printer. Okay, and so on. So this way there may be a big graph, directed graph, dependency graph. And if there is a cycle in the graph, so in a directed graph, cycle means it's a basically closed directed path. So if it start from a vertex say P1, then P2, then P3, then it coming back P1. So that means if in the cycle actually everybody is waiting for others to compete. So it's a infinite loop, right? It never actually get the time. Actually always everybody is waiting for somebody, right, in the loop. So that's a cyclical dependency. And in operating system, actually, we learn these things are called the deadlock. When deadlock occurs, none of the process can execute and proceed, right? So that's why we actually remove the deadlock, and we make this dependency as a cyclic graph. Okay, and after that you can give a topological ordering of those processes, so that which process has to be executed first, which process can be executed independent of others. So those can be seen also from the topological ordering. Okay, so this is a direct application of topological ordering. There may be some other. Basically, when you want to you have multiple say in a factory, when something is produced, some product is produced, there are different units that do something, right? So one unit may be independent of other, depending on on others. So basically this managing those processes, which in which sequence these different steps has to be executed, so that final product can be given. So that is another example where topological sorting is important. So here is an example that I took from the reference book, that some to wear some different dresses in the morning, and it can be under shorts, pants, belt, shirt, tie, jacket, socks, shoes, watch. And this arrow says that say socks has to be wear before the shoes, and watch is independent. So there is no dependency of wearing watch uh, on any other part, right? So we actually given one graph over dependency graph over here. That's a directed graph. So an arrow from a vertex U to V means you have to be far from before uh, the vertex V. And so in the topological ordering, U has to be come before. So wiring belt will come before the jacket, or wiring shirt will happen before the wiring belt. I have a phone call. I'll talk. Unmuted again. I am muted. Oh, sorry. Yes, I unmuted, but somehow is didn't work. That I thought I unmuted it. So fine, fine. So I'll continue from there again. Then I didn't realize that. Okay, so we are back to that point again. So from the definitions. So basically, we want to sort the vertices uh, in such a way that, say, we put the vertices on a line, on a real line, so one after another, in such a way that there may be an edge from a vertex u to f, u to v. From a vertex u to v, there could be an edge, but there cannot be an edge from v to u. So in a forward fashion, the vertex could be from left to right, but there cannot, sorry, there can be an edge from left to right, but no edge can be there from right to left. Okay, that is illustrated here. So all the vertices in this representation of the wiring different dresses are basically shown over here. So dependencies are shown by arrows. Forward arrows tells a dependency that socks has to be wired before the shoes, okay, and so on. Similarly, shirt has to be wired before the tie, and so on. So this arrow tells the dependency, and these arrows, actually the edges can go from left to right in this linear order of the vertices. Okay, so in fact, if we do a depth first search in the graph, the finish times give a linear ordering of the vertices if that ordering exists. So in fact, when the graph is not acyclic, if graph has a cycle, then this ordering is not possible, ordering is not defined, it doesn't exist. Okay, so that I was talking about, there is a deadlock in the uh, there is a deadlock in the process, in the operating system. If there is cyclical dependency, that means there exists a cycle, uh, then the deadlock occurs, no process can actually execute, they stall, actually they just wait for others to complete. So so their topological ordering is not present there. So in order to solve that and find the topological ordering, so basically we do a depth first search on the graph. Okay, so that will give every vertex as finish time f. For every vertex u dot f is the finish time, and now the vertex which is finished first, it has the minimum finish time, right? So that's why we put it on a linked list, okay, in the front. Again, next time when discovered another vertex, we put it on the front of the linked list, so that every time as soon as we finish one vertex for exploration, we put that vertex into the linked list one by one. So that will give a linear ordering of the vertices. And if we finally, when it's completed, the DFS and all the vertices are in the linked list, so front element will have the maximum finish time, so next element will have the next maximum finish time, and so on. So this will, if we just put the vertices in the uh, reverse ordering, that means the finish time maximum is, it will come first, then the next maximum will come next vertex in the linear ordering, and that will be a topological sorting. And in this algorithm, it is assumed that the graph doesn't have a cycle, so that's why there the topological ordering exists. And in case the graph has a cycle, suppose when you give an input graph which may be acyclic or may not be acyclic. So if it is not acyclic, it has a cycle. So during the depth first search, you can identify the cycle by determining whether the graph has a back edge or not. As soon as there is a back edge, so you can report that topological ordering is not possible, so you exit from there. Otherwise, at the end of successful execution, actually you can get a linked list of the sorted order of the vertices. Okay, so this algorithm entirely depend on the DFS algorithm. So DFS algorithm actually runs in linear time in number of vertices and number of edges. So this can be executed in, so first line, that DFS, that takes linear time in number of edges and number of vertices. Again, when you construct the sorted order, actually you insert to the linked list, right? So and the front of the linked list, so this will take, for every insertion will take constant time, right? So if you remember the linked list operations, insertion in the front will take constant time. So inserting n many vertices will take linear time. So this says that total time for topological sorting will be in linear in number of vertices and number of edges. Okay. So here one important characteristic that's I just wanted to just give a proof on that, very simple one. So a directed graph G is acyclic if and only if DFS of G yield no backage. So basically when the graph is a arbitrary graph is given, so you have to make sure that when you compute the ordering, uh, there is no backage. Okay, that's I just told you that you have to test for it. So during DFS you can do it. So here just a proof of that. So suppose the DFS produce a backage. Okay, then we say that there is a cycle. So that means that is not acyclic. Graph is not acyclic. And in the reverse way, if it's contain a cycle, then we will show there is a backage. So this is an if and only conditions for the G has to be cyclic or acyclic. So if there is a backage, there is a cycle. If there is no backage, it is acyclic. So suppose DFS produce a backage called x comma v that is shown in the figure. So then V is an ancestor of the vertex x. Ancestors that you can determine that when you look at the adjacency list of x, and one of the adjacent vertex is V, which is already discovered and is an ancestor of x because its uh, the finish time is is the discovery time is much before the x, so it is already discovered and it is in the same component that trace out by the DFS. So it's x is the x is a reachable vertex from u, v is also a reachable vertex from u, and they have different discovery terms. So this give you a basically backage. Okay, so this is if you just complete this as v y x, so basically that's complete a cycle. So v is an ancestor of x, x is a descendant of v, right? In such cases there is a cycle. Again, suppose s is a cycle, suppose that cycle we denote by s. I think there is a typo, I have used c here and use s here, so maybe you can use s everywhere. So suppose that cycle is s and we show that a depth first search G yield a backage. So V be the, so since S is a cycle, there is a start vertex. Suppose V is the start vertex of the in the cycle. So cycle means is a closed path. Is a closed path. So that means it start at a vertex V and end at a vertex V. So while it end at the vertex, so there has to be another vertex from which there is an edge. Okay. So if that just x is the just preceding vertex in the cycle S, so then x comma v is an edge that. So then the time v dot d, the discovery time of v, the vertices of S forms a path of white vertices of v to x. So when the v was discovered, so its descendants are not discovered yet, so that means those are white vertex. So that basically give a basically path that consists of all the white vertices. That means basically this x is a descendant vertex in the depth first forest. So then x comma v will be a backage. It's very immediate actually if you just interpret the figure. So that is also same example is here, that cycle that v y x, and in this case x is a descendant and also x to v will form a backage. Okay, and using that theorem also we can prove that the topological ordering is happened, the ordering given by the topological sort algorithm, topological sort, that algorithm here, this algorithm. So this algorithm gives a topological ordering that we want to find out. So topological sort produces a topological sorting or ordering of the directed acyclic graph provided as input. So if you give an acyclic directed graphs, then this algorithm topological sort will give the topological ordering of the vertices. So here actually we use this lemma here, and some properties of this start time and the basically finish time here. So using that finish time, we can argue that there is no edges from v to x. Say suppose v is shoes over here and x is your socks. So v to x, if x appears before v, okay. So otherwise there will be a cycle because it is acyclic. So there is no back edge and there cannot be such edges also. So that I leave you to just go through once and convince yourself that yes, it provides the topological ordering of the vertices. Okay, it's a very simple one. You can just read about it. There is some other things that we can also compute some other characteristics of the graph from the by using DFS traversal. So and also BFS traversal that we have seen, we can classify the edges by using breadth first search, using depth first search as well. But especially for the BFS, we can also use, we can also extract some property like called articulation point, breeze and biconnected components. So if you look at it, at your hand, that your fingers are articulated. So articulation point is basically the joints. Those are, you can think about vertex, like your arm, like at the wrist there is a joint, right? There is a elbow, there is shoulder, there is a joint. So all those joints are basically articulation. So similarly in a graph, you can think about the articulation points also. So if you remove the vertex, graph become disconnected. So that's called an articulation points. And if you remove an edge, then G also will be disconnected. So that is called a bridge, because is make a connection between two part of the important part of the graph. Okay, so that's is called a bridge. And there are some connected, there are some components, some subsets, subgraph of G, such that even if you remove uh, one edge from it, still it will be connected. Say if you think about a cycle in a graph. So cycle in a graph means they are biconnected. There is a two alternative path between any two vertex of the in the graph. Okay, suppose you consider a cycle. There are, cycle is a closed path, so there are vertices in that path, and you remove one vertex, one edge, then still that is connected because there is alternate path. Is something similar to that concept of tree. If you add any edge between any two vertex in the tree, then that will be a cycle. So and if you remove one of the edges in a cycle, it will be disconnected and still become a tree. So such components of G is called biconnected components, because each of the vertices are connected by two paths. So just like here in the figure, that all the black shaded vertices are called the articulation point. So when you remove these black vertices, then it will actually disconnect all other vertices which are uh, which are which are forming a basically biconnected components. And even the shaded edges, if you disconnect the shaded edges, then graph will be disconnected also. So these significant of this articulation point or bridge or biconnected components can be used for many applications, especially if nowadays there is something called social network analysis. So in a social network analysis, that we want to determine the community, close community. Close community means there are people who actually interact with themselves. So you have a friend circle, you make a group of Techno India University students. So maybe your sections have a different community, right? In Facebook, maybe in WhatsApp and all. So that make a community. Another, maybe you have a friend in other university, they have another group, and you have a friend in their group. So basically you will be one contact person to another contact person in that group of student in the different university. So basically, uh, if we remove these connections between you and your friend for in other university, then these two community will be disconnected, right? So that's why you are very important here in a social network also, that different operator, service provider, or uh, says Amazon, or maybe Flipkart, or many other business who are doing business, an online business basically, or any business. So they want to motivate people to buy their product. So they want to motivate people through the network, social network. Nowadays every day you see there are ads are coming to your Facebook account. So that's what they're doing. They want to influence some of the people. It may not be possible to send those ads to everybody. They want to motivate only one person. Who should be the one person? They want to find out some person who is influential, which are connected to others, very important person, so called the social VIPs. Some people say social VIPs. They identify the social VIPs. Those are basically these articulation points in the social network graph. And also there are different criterias. Who is that person? Maybe that person is a big shot like Bill Gates. So if Bill Gates says something, even it is not acceptable, sometimes many people won't accept, but since Bill Gates is saying, they just don't think about, okay, he's good, he's saying something, so we should follow it. So that is the way it happened every day. Even very wise person also fall into this trap. So that's they're taking. So you see there the graph theory is used there. Extract some information from the social network. So extracting the information is basically called the data mining. So from the social network data, the extracting the informations, and how that information has to be used. Suppose a particular company, they are doing business, they based on this extract information, they take some decision. So what decision they should take? So from the data or the information extracted from the data, they take some decision, business decision. Okay, so that's called business intelligence sometime. In general, that is called a data analytics. So there is a difference between machine learning, pattern recognition, data mining. Data mining is basically, it's a phrase used for uh, performing many tasks: pattern recognition, task classification, clustering. Uh, uh, there are regression analysis, that forecasting, all these kinds of things. So the group, everything is grouped into these particular things called data mining, and then based on the information that mined through those the data and used for business intelligence and business decision, that's called data analytics. So always remember this difference. Okay, so there, for social network analysis is so important nowadays. You can do a lot of things there. So information is power, and actually now that information used by many, even for the uh, election, political election campaign also, they are using those things behind us, they are influencing us. So it's so powerful. Okay, so I leave you to here. I have given that book. You can look into that chapters 22, elementary graph algorithm, Gorman's book. So in page number 621, this articulation point, these pi connected components are discussed there, and there are some uh, you know things that hints are given how this can be identified in a graph using DFS or BFS traversal. So you should go through it once at least to have. Okay, so So that's all for the elementary graph algorithms. In fact, I wanted to do about strongly connected components of directed graph, um, but we have to do some other algorithm also, minimum spanning tree and shortest path. So shortest path, actually there are different type of shortest path algorithm or problems as well. So probably I will not do the all pair shortest path algorithm because that require dynamic programming formulations, and in your algorithm design course in the next semester you will learn that. So that takes some time also, but here we learn the greedy algorithm, especially will be used for minimum spanning tree computations and also finding shortest path, single source shortest path problem. So some algorithm like this algorithm I'll cover in the course, and once it is done I want to complete some of the things that we left out, say planar graph and graph coloring. That two thing I wanted to do, that's very important. And at least two class for combinatorics. We may not have much time, we'll see that how much we can do. Okay, so I just I have some time today, so I will just introduce minimum spanning tree, basic definition, at least the generic algorithm that we want to do. Do you have any questions from depth first search, or any questions or any doubt from the part we have discussed today? Any of you have uh, any doubt? Maybe I can go through once. I'll just take a screenshot. So I saw in the first session more than 40 students joined, but many students were very late. Why it is so late? Its class is starting at 10 o'clock. It's not at 8 o'clock in the morning. So if it is 10 o'clock, then it should not be so late. Uh, okay, so you have no doubt, I guess. If you have any doubt, you can write in the Google Classroom. So let us give some idea about spanning tree, some motivations. So consider designing of electric circuit. So there are many components are there, so there are many pins maybe that has to be connected by wires. Suppose there are n number of pins, and uh, you want to connect by them by wires, so you want to minimize basically cost for connecting them. Okay, so you can formulate this as a graph theoretic problem and finding minimum spanning tree. So spanning tree, again, I just tell you many time I discuss about spanning tree. So spanning tree of a graph. So suppose graph is connected. Spanning tree is basically it's a subgraph of the graph such that it contain all the vertices, and it's a minimally connected subgraph basically. So basically it's a tree. It's a tree. It's a subgraph. It's a tree and containing all the vertices. So if you pick up some of the edges, okay, of the tree of the graph, and you span the a computer spanning tree, the spanned by the edges that you have selected. So basically you pick up n minus 1 edges of the graph so that it span the graph. So it obviously it contains all the vertices, and also it will form a tree. So that's called a spanning tree. And in our this problem, say when we have say n many pins that we want to connect by some connecting wires. So every the edge, possible edges between any pins basically give you an edge, right? So those edges, suppose we have some edge set of edges that possible interconnections between pair of pins, and also every connections has some cost. So in a circuit there are some metals that use is very precious metals, right? Like Gold is used there. Gold, copper mostly, for, not used much. The gold is also is for very delicate circuit design, and also platinum. So that's why whatever metal you use, basically you want to minimize the cost. Okay. So uh, objective is to find a acyclic subset T, which is a subset of E, that connects all of the vertices, and the total or the total cost is basically minimum. So total cost means how many edges are there and their weights. Weights means the cost, some money there. So W comma V is basically some money that required to construct that particular connections. And you take sum of all those cost of all those edges, that is in the T. Okay. So that's our objective. So basically it's a combinatorial optimization problem. Optimization means you want to minimize something subject to certain conditions. The condition is that it has to be a spanning tree, and also the weight for the tree. Weight is the sum of all the edges, edge weights. Okay. So that is basically objective function, and this is a discrete optimization problem. It's not a continuous optimization problem that you can differentiate and make the derivative to zero, find out, and this thing. This is a discrete setup, and you have to consider different combinatorial cases. That out of the combinatorial cases, you have to pick up one of them that will give the minimum value of the weight of this particular tree. Okay. So in discrete optimization problem actually solved by different algorithm, and one is called the greedy algorithm, another is called dynamic programming, and there may be some other linear programming problem, integer programming. There are different type of techniques are there. Here we'll be using greedy algorithm. So what is a greedy algorithm? So I'll come to this point later. So let us give the formal definition of minimum spanning tree. Suppose G is a graph with vertex set V, S set E, and a weight map. So W is a mapping of each edge to a real number. So it is a function from E to R. That means for given a edge U comma V, W of U comma V is a basically some real number. It could be negative, it could be positive, it could be zero, anything. And now a spanning tree T of G. So it's a minimally connected uh, subgraph of G containing all the vertices, right? So that's a spanning tree of G, uh, such that yes, it's a spanning tree. So if you just a spanning tree, that's enough actually. So this spanning tree T of G is called a minimum spanning tree if the weight of T is minimum. That is, the weight of T is less than equal to weight of T prime, where T prime is any other spanning tree containing all the vertices of G. So that means there may be multiple spanning tree also, minimum spanning tree. Multiple spanning tree can be there. For example, here that given graph below, that all the shaded edges, if we pick up the shaded edges and the vertices of this graph, it is a spanning tree. Okay. And also it is a minimum spanning tree, and total weight is 37. If you add the weight values that are written just close to each of the edges, so this weight value W comma C is 8, W of C comma D is 7. So these weight are written just beside the edges to denote the edge weight. And if you sum up these, it will be 27 for all the shaded edges here. Okay. And this is one of the MST. There could be another. Think about that immediately, that what if we remove the edge B comma C and add another edge A comma H. So in fact, if you remove the B comma C, then what will happen, that it will create two connected components. So it's not a tree. but you can add a comma h also. Instead of b comma c, you can add the a's a comma a's in the spanning tree. So it will be another spanning tree, but the total weight of the edges in the new spanning tree is same, because we just replaced one of the existing edge of the spanning tree with another edge which is the same value, right? So there are two, at least I can see there are two such minimum spanning tree with same edge weight. Okay, so minimum spanning tree is not unique. So how actually we compute the minimum spanning tree? So suppose we have the connected undirected weighted graph with weight map w. Sorry, there is a typos over here. It should be w from e to r. So objective is to find a spanning tree, and we have two standard algorithm that we use called Kruskal algorithm and Prim's algorithm. And before going to those algorithm, we just learned the basic idea, the fundamental idea that is used to design Kruskal algorithm or Prim's algorithm. Okay, and that all these two algorithms are based on a particular strategy called the greedy strategy. And that greedy strategy means basically we add uh, one edge or one vertex at a time and we grow the tree. We basically, when we add an edge, basically that's called some edge called safe edge, which has the minimum weight, as well as it will not create any cycle. Okay, so a greedy approach is used. I can give you another example of a greedy strategy. Is basically try to minimize by looking at the local